Welcome to Backend Engineering. Have you ever really stopped to think about what's happening inside your computer when you compile code or fire up an application? Well, you're in the right place. Today, we are going to build a modern PC from the ground up, component by component, so you can see exactly how it all fits together.
Right? It's so easy to just see it as this magic box. But what's inside is really this incredible ecosystem of highly specialized hardware. So let's pull back the curtain and demystify the actual components that power every single line of code you write.
So here's how we're going to do it. We're going to follow a logical build process, just like we're putting it together for real. We'll start with the foundation. That's the case and power supply. Then we'll install the motherboard, add the brains, give it some vision, and wrap up with its memory and its life support system.
All right, let's get into it. Every great building needs a solid framework and a source of energy, right? Well, for a PC, that all starts with the case and the power supply unit.
The case is way more than just a pretty box. Seriously, think of it as the computer's skeleton and its skin. It provides the physical structure, sure, but it also protects all those delicate electronic organs inside from things like dust and static. And maybe most importantly, it's designed to manage airflow, which is crucial for keeping everything cool.
Now, if the case is the skeleton, then the power supply unit, the PSU, that's the heart. It takes the alternating current from your wall outlet and converts it into the stable, low-voltage direct current that all the components need to survive. And for developers, a good PSU is non-negotiable. Trust me, a cheap one can lead to random crashes and corrupted data. That's a developer's worst nightmare, especially when you're trying to keep a server stable.
Okay, so our case is ready. We've got power. Now it's time to install the thing that connects, well, everything. This is the motherboard, and you can think of it as the computer's central nervous system. And yeah, the slide just nails it. It's the backbone of the PC. It's basically this giant, complex circuit board that acts like a superhighway of electrical pathways, or buses. It's what allows every single part, from the processor to your keyboard, to talk to each other. This slide here is basically a map of our computer's downtown district. You've got the CPU socket, which is where the processor lives. You have RAM slots for memory, and you have expansion slots. As a developer, you're going to be looking at stuff like the number of RAM slots for memory-heavy apps and the speed of those PCI Express slots, which dictates how fast your GPU or your high-speed storage can communicate with the CPU.
All right, our central nervous system is in. Now we need to give this machine some actual intelligence. It's time to install the brain, the central processing unit or CPU, and its super-fast short-term memory, which is the RAM.
Okay, so a lot of people get these two mixed up, but they have totally different jobs, even though they can't work without each other. The CPU is the active thinker. It's executing instructions, doing all the math. RAM, on the other hand, is like its high-speed workbench. Let me give you an analogy that makes it crystal clear.
And this is why it's so critical. When you run a program, all of its instructions get pulled from that slow, long-term storage into this lightning-fast RAM. For back-end work, having more RAM means you can run bigger databases, more virtual machines, or handle more users at once without your system grinding to a halt. It's the difference between a snappy app and one that's always waiting on the disk.
So our machine is thinking, it's remembering, but it's blind. It can't show us a thing. For that, we need to install its visual cortex, the graphics processing unit, or GPU. See, a CPU is kind of like a jack of all trades. A GPU, it's a master of one thing, doing a ton of simple calculations all at the same time. This is called parallel computation. It's amazing for drawing graphics, but for modern back-end engineering, it's absolutely essential for things like training machine learning models or crunching huge data sets. So you've basically got two choices here. Look, if all you're doing is running a code editor and a local server, an integrated GPU that's built right into the CPU is probably fine. But if you're even touching machine learning frameworks like TensorFlow or PyTorch, then a powerful discrete GPU isn't a nice-to-have. It's absolutely essential to get anything done in a reasonable amount of time. All right, we're on the home stretch. To finish our build, we just need two more things: the system's long-term memory, its archives, and the life support system that keeps it all from melting down. This is the computer's library. Now remember, RAM is volatile. It forgets everything as soon as the power goes out. Storage is non-volatile. It keeps your operating system, your apps, and your precious code safe. This choice is huge for a developer. Running your OS and your entire dev environment on an SSD means way faster boot times and lightning-fast code compilation. An old-school HDD is fine for cheap backups, but for day-to-day productivity, SSD is king.
And that brings us to the last, and I mean critical piece of the puzzle, cooling. All this amazing hardware generates a ton of heat, and without good cooling, your components don't just crash, they start to thermal throttle, which means they deliberately slow down to avoid cooking themselves. For a long compile or machine learning job that runs for hours, good cooling is what guarantees you get consistent performance.
So our virtual build is done. Let's hit that power button and see what happens. First, the PSU sends power to everything. Then, the motherboard's firmware runs a quick power-on self-test to make sure all the hardware is working. If everything checks out, it finds the operating system on your storage drive and loads it into RAM. And finally, the CPU takes over, starts executing instructions, and your desktop appears. It's alive!
Hey, if you found this breakdown of a PC's anatomy helpful, do me a favor and hit that like button and subscribe to Backend Engineering. It really helps us figure out what kind of tech explanations you want to see more of. So, the big takeaway here is that building a computer is really just a series of trade-offs, right? Do you invest in a monster CPU for faster parallel builds, or do you pour that money into more RAM for large-scale simulations? Do you need the raw speed of an SSD for your database, or the raw power of a GPU for machine learning? Each choice you make defines what that system is for. So what would you build? Thanks for watching.